CP here, and welcome back to Help I'm Teaching, where I help you teach something whether it's the first time or the 100th. I give helpful analogies, answer common questions, and debunk misconceptions. After last week's sudden departure to psychology, we're back in my wheelhouse. Before I ever took a class in botany, I took a class in pedology, or soil science. I recommend you watch the first episode on photosynthesis, because these two go hand in hand, and there are a bunch of things I addressed there that I should have addressed here, but clearly I got excited. Now, soil probably isn't what students think of when they think of science, but it's a foundation for pretty much any food item you can find at the supermarket that isn't seafood. It's a cross between biology, ecology, geology, and chemistry, and it can help us understand where we came from and where we're going. You could start by dropping a spade load of soil into a clear plastic cup filled with water. Just let it settle for about a day, just by yourself. You should see the soil separate into 3 layers, or horizons. If you have the time and locations, try doing this in 3 different cups from 3 different areas, all at the same time, and show your students. They'll really be able to see the soil horizons and how they differ. Ask them, what do they think is happening? Why are the width of the soil horizons of each area different? The answer is that this is the soil's unique texture. Classifying soil texture is a big deal. There are 3 different sizes of particles in soil. From biggest to smallest, we have sand, silt, and then clay. When they're all suspended in water, the biggest particle sinks first, and so on. So in the cups, the lowest layer is sand, the middle is silt, and the highest is clay. There's a triangular chart you may have seen with the words clay, sand, and silt across the sides. This is the soil texture classification chart, and you can figure out what texture your soil is by comparing the layers. For example, if the first layer is about half and the other 2 are about a fourth, you'd find where 50% clay meets 25% sand and 25% silt, which would give you a clay loam. If your students are math inclined, you could always try a worksheet where you give them the percentages and the chart, and they tell you what kind of soil it is. Sand is the biggest texture size and drains well, but also can't hold on to nutrients easily. Clay can hold water and nutrients very well, but their small size means they can compact together very easily, trapping too much water and not leaving space for air or root growth. Silt is a happy medium. Soil has lots of nutrients to help plant growth along, and hold on to them until they are taken up by an organism. Soil particles are usually negatively charged. If they know anything about chemistry or even magnets, you can remind them that opposites attract. And what's the opposite of negative? Positive. For this reason, most nutrients that stick to soil are positively charged, or cations. K plus potassium, Ca2 plus calcium are good examples. Cations are positive ions, so I like to remember this by thinking that cats are a very positive thing. There are plenty of nutrients plants require, but the 3 most important are N, P, and K, or nitrogen, phosphorus, and potassium. These are known as plant macronutrients, while the things plants need in much smaller concentrations like iron, molybdenum, and boron are known as micronutrients. In fact, micronutrients in just slightly higher concentration than ideal can poison your plant. More on that later. It's important to think of soil as alive. Not like how a bird is alive, but like how a forest is alive. Not just the life you can see like bugs and worms. A healthy soil should have all kinds of fungi and bacteria as well. These are all known as decomposers and break down organic matter in the soil. These organisms all secrete things that bind soil together in certain shapes. These are called soil aggregates, and you can see them for yourself as a little crumbs if you shovel some soil into your hands. Soil aggregates are important for good aeration, drainage, root growth, and worm activity. A healthy soil should have lots of organic matter as well, which is exactly what you think it is. Dead leaves or roots, bones, feathers, and rotting fruit are all examples. These are consumed by decomposers and excreted into a form that plants can take up. A healthy soil should also have plenty of plant roots. These hold the soil together. If soil has no roots, it can be easily swept away in a flood or wind. Ever got earbuds tangled up and spent too much time separating them? Plant roots can be like those earbuds, twisting around the soil, and when wind or water comes, they hold the soil in place. Plant roots also secrete mucilage or root exudate. Root exudate does a lot of good for the soil. It promotes beneficial bacteria, makes nutrients easier to uptake, and even allows roots to recognize whether other roots come from the same plant as itself or not. Even dead plant roots are a form of decaying organic matter that releases nutrients. Soil also contains organisms that associate with plant roots, like fungi that grow on them to help them uptake phosphorus, or bacteria to snatch nitrogen out of the air. More on that later. One of the most important functions of soil is to store carbon. Photosynthesis takes carbon dioxide from the air and turns it into organic compounds in plant roots or tubers underground. These, as well as the animals that eat them, keep the carbon in the soil. Even when they die, they are consumed by soil organisms and the carbon remains in the soil. If this decomposition happened above ground, it would release some of that as carbon dioxide back into the atmosphere, which is not good for climate change or the ice caps. Frozen soil that doesn't have actively decomposing material is called permafrost. The reason we don't want these to warm up is that cold halts decomposition, but if it got warmer, the soil organic matter would decompose, release carbon dioxide into the atmosphere, and make climate change even worse. Here are some common misconceptions about soil. Even though silt is a happy medium, it's not always the best soil to grow crops in. Some plants like lavender prefer a very sandy soil. Others like roses grow in very clay soils due to deep roots. Always do research on what you're growing and what conditions it likes. The differences between sand, silt, and clay particles are really just size. They're the same material, ground up rock. However, there is a difference between soil and dirt. Soil describes a functioning ecosystem, so we can think of it as a bustling city. Dirt is basically that same city, but completely empty. The sand or clay particles are still there, it's just that no one's home. Dirt is dead soil with no ecosystem. This can be caused by deforestation, overgrazing, construction, overfarming, or other human practices. Not all plants need soil to grow. Aquatic plants can be rooted to soil, but they can also be free-floating, like duckweed. Pothos, a really popular houseplant you can find just about anywhere that sells plants, is famous for being able to grow thick roots in a jar of nothing but water. These plants get their nutrients from the air. There's a trade-off though. It's very difficult to get pothos to bloom flowers. I talked a bit about this in the pollination episode, but flowers are a way to take advantage of the local wildlife to disperse seeds and help pave the way for the amazing variety of plant life that we see today. In the absence of flowers, pothos has other advantageous traits. Every trait of an organism, like feathers, leaves, scales, or spines, costs energy to develop and maintain. Pothos originated in Asia and Oceania, where it can be very humid and monsoons are common, so reproducing in the water just works for them. You might have heard that members of the legume family can use bacteria to fix atmospheric nitrogen to a form usable in the soil and fertilize the soil around them. This is true, and I want to add the caveat that it's not just legumes that can do this. Cucurbitalis, or the order of plants including squash, can do this as well, but through a different mechanism. If you have time and space, you can try this out in your class by leaving 2 identical patches of soil, planting some more peas in one, and watching how weeds grow. After a few weeks, the pea plot should have more growth because the pea roots are adding more nitrogen to the soil. Sometimes, fungi can grow into or around the roots for food, and surprisingly, this is a good thing for both of them. The fungi receives carbon compounds from the roots, and the roots can now uptake phosphorus more effectively. These are called mycorrhizae. Myco meaning fungi, and rhizae meaning root. Plant roots acidify soil. If you've ever heard that plants eat rocks, this is how. This makes nutrients more available and weathers hard minerals. This is why the suggested ranges of pHs for plants, 5.5 to 8.5, leans towards more acidic. These secretions create an area around the roots known as the rhizosphere, which is more acidic than the surrounding soil. If the soil gets too acidic for the roots, they can secrete root exudates that make the soil more basic. Now, here are some questions. Why do people care about worms so much? They eat decomposing material and excrete it as nutrient-rich castings, but there's more. Their castings contain beneficial soil bacteria from their guts. As they wriggle through the soil, they also create channels for water and air to run through. One study I found showed that they account for 2.3% of the world's legume production and 6.5% of the grain. However, not all worms are good for the soil. If worms are from a place with different soil conditions, they could alter soil to be more like their home and drive out the local worms, which can be disastrous for native plants and animals. In North America, there's the Asian jumping worm, which outcompetes native worms and stresses native trees. Are there any soil nutrients that aren't positively charged? Yes, probably the most important ones. Nitrogen can be found in the cationic form of NH4 plus or ammonium, but is more commonly found as NO3 minus or nitrate. This means that unlike other nutrients, nitrate is not attracted to soil particles and is actively repelled by them. The same is true of phosphorus, which is often found in negatively charged phosphates in the soil. If you've ever heard never to water a plant after fertilizing, or to never fertilize before a rain, it's because the water will wash the nitrate and phosphate out of the soil and send it underground or to nearby streams. And excess nutrients in water is never good. This can cause algae to grow explosively and produce toxins that kill sea life in what's called an algal bloom. This is what causes aquatic dead zones you might have heard about, like the one in the Gulf of Mexico. In some cases, soil can be positively charged. This means that nutrients like nitrogen are now the ones binding the soil, and the cations are washed away. Why can nitrogen be found in all these different forms in the soil? To keep it very simple, nitrogen is always moving in a cycle, and at every given time or area of soil, you should be able to see multiple parts of it. For example, wouldn't it be strange if all the water in the water cycle evaporated in the clouds, and all of it came down as rain at the same time? It'd be weird if we couldn't have a pond and clouds at the same time. Why is it important that nutrients are positively charged? Aside from what I mentioned earlier about opposites attracting, there's something known as cation bridging. Some cations like magnesium and calcium have two or more positive charges. Since soil particles are negatively charged, they can sandwich these cations, attaching to each positive charge. And if the soil particle has multiple negative charges themselves, they can attach to another magnesium or calcium, which in turn could be connected to another soil particle, and so on. This is a mechanism by which soil aggregates can form. If this sounds confusing, think of calcium or magnesium as a glue that can hold lots of soil particles together. Can humans eat soil and gain nutrients from it? Actually, yes, but it's not a good idea. Eating soil, or pica, is a symptom of iron deficiency in children because they're trying to get iron however they can. Soil has microorganisms and toxic metals that could get you really sick though. Nutrients can also be in forms that our stomachs can't absorb, and we require them to be converted by a plant or animal first. It's like trying to power a modern-day car by throwing wood and a match inside the gas tank. Best case, it's not going to work. Stick to supplements or eat food. How do metals affect plant growth? In certain conditions, like the pH being out of the 5.5 to 8.5 range, toxic metals can become more available for plants to uptake. For example, aluminum, which appears in acidic soils, greatly interferes with roots and photosynthesis. Manganese and copper are normally micronutrients, but in basic soils can accumulate and disrupt seed germination. We can improve metallic soils by planting bioaccumulators, or plants that specialize in collecting toxic metals before we plant our crops. We can simply dispose of bioaccumulators in the compost, or sometimes we can even smelt them to recover the metal. Can you turn soil of one texture into another, like grinding up sand to break into smaller clay particles? Well, no, you can't. These were created based on very specific geological conditions over millions of years, stone being weathered down by the area's wind, water, and ice, and the closest you can get to this is to just replace the soil in an area entirely. You shouldn't bother going through all that, though. Your efforts should just go towards building organic matter, and you should be fine. Why are soils sometimes colored red? You might have seen soils that are a bit differently colored from what you're used to. Soil can turn red if it drains fast or it is in a dry climate, which is why you can see it in deserts. This color change is caused by iron in the soil. In other climates, iron can cause soil to turn yellow or even blue. Why is erosion bad? Isn't the soil just moving somewhere else? True, but it strips away the topsoil, which can contain lots of organic matter, meaning the soil will be less fertile. It destabilizes the soil aggregates, which can make aeration harder. And if the fertile soil ends up in a body of water, it can cause algal blooms and aquatic dead zones. You want your soil to remain in place so it can build itself up over time. Would you like to spend months building a house, getting food, learning the neighborhood, only to have the whole thing blown down by a drizzle? That's how worms feel when soil erodes, so take care of your worms. What does it mean to build soil? I mentioned earlier that soils are alive and can die. Building soil is a process of reviving the soil ecosystem through regenerative agriculture practices. I'll go over a few different practices. Mulch is an element of building soils. It's a layer of material on top of a farm plot that keeps the temperature stable, suppresses weeds, and traps moisture. Think of it as a blanket. It can be organic like dead leaves and wood chips, but you can also use plastic and fabric. Organic materials are better in a lot of cases though, because they'll decompose and add more nutrients to the soil over time. It's like a blanket but made out of food. Crops use different nutrients in different amounts from the soil. If you kept growing the same thing over and over again on a plot, you'd exhaust the soil of all those nutrients. This is known as monoculture or factory farming, and uses a great deal of resources to artificially keep the soil healthy. To get past this, farmers can plant different crops in a plot after each harvest, or even leave a plot to rest for a season. Ask students to imagine a candy store that receives shipments every month. Out of the dozens of types, people only buy caramels all year. Caramels run out very fast and the owner would need to keep ordering more at extra cost. Meanwhile, other candies like jawbreakers and bubblegum would accumulate. But if people bought caramels one month, then jawbreakers next, then bubblegum next, the supplies would remain at a good level and the owner would be very happy. Sometimes the best way to build the soil is to just leave it alone. Once you've set up your mulch and got organic matter in the soil, you can let nature work its magic. You don't need to disturb the soil or water it every day. Try not to even walk on it, as this might compact the soil. Bacteria in the soil will begin to decompose the materials, the soil microorganism community should grow, and the insects will move in. After about 2 weeks, you should be able to plant whatever you want. After going through all these things with students, it would be fun to ask them to come up with their own farm plan. What do they want to grow? What methods do they want to use? Where? I'm sure they could come up with some of their own ideas for farming practices you may not have even thought of. They always say the best way to teach is to do, so if you're lucky enough to have access to a garden, you could try making experiment plots where one plot uses, say, organic mulch, another uses plastic, and another has none, or one is walked on every day and the other is left alone. Beans grow fast, so they're always great for these kinds of observational experiments. Try to have your students eat what they grow. It'll make groceries less of an unknowable black box, and they'll feel like they can produce food without buying it. This in turn can help them separate themselves from the inescapable modern-day economic system and maybe, just maybe, help them dream of a better radical future. That's all I have for today. Thanks for listening. I now have a Twitter at HelpI'mTeaching. Transcript and sources are in the description as always. See you next time and keep teaching.